Okay, so on this problem, I've got a cantilever beam with cross-section shown there, uh, loading as shown there, and I want to find the maximum tensile stress and the maximum compressive stress. So I want the tension and the compression on this thing. Um, and all the stuff for the area is given, neutral axis, area moment inertia, that sort of stuff like that. So again, my equation that's going to define everything is my flexure formula, which is mc over I to find the normal stress. Okay, so first thing I need to do is figure out where the maximum moment is. Okay, and that maximum moment is going to occur at the endpoint, which hopefully is clear just kind of by inspection. That's where the most moment is going to be 0 over at B, maximum over at A. So really I'm just finding what that moment is just using statics. So I'm going to, sum the moments about A. I don't want to forget my moment that I'm looking for. That is the reaction moment. It's also going to be the maximum internal moment that I'm going to have. And that's going to equal 5 times that 200. Again, that'll be negative. It's not going to equal that. I'm going to have that. Then I'm also going to have a negative. It's at the center, so that's 4 feet away. And then that's going to be 8 feet long by 20 for that distributed load. Okay, and that's the moment of that distributed load given by that. So from that, I can find that my maximum moment at point A is 1640. And of course, all of this was in pounds and feet. So I'm going to want to remember that. I want to move this all to pounds and inches. I'll do that up at the equation that I'm about to apply. Now, in order to find, say, the maximum tensile, okay, I'll do this one right down here. So to find the maximum tension, it's going to be under tension on the top as this thing bends downward. The top's going to elongate, go in tension, and the bottom's going to be in compression. Okay, so C going to the tension will be to the top, which will be the 0.606. Okay, it's still going to be that moment I just found, 1640. Of course, I need to multiply that times 12 to go from pound feet to pound inches. And then I'm going to take that times, again, the distance to the top where the tension is actually occurring. And that's going to be 606. Okay. Again, the moment of inertia is given to me. It's 2.81. Okay. So from that, I can calculate that the max tension is going to be 4.24, and that will be KSI. Again, I converted my foot-pounds to inches to get that. Okay, so the maximum compression is going to be at the bottom again, because as it bends down, that bottom is going to be pressed in and contracted, right? So the only thing that changes here is that C value, which will go to 2.133. So again, my moment is going to be 1640. Take that times 12 to get it into inches. And again, my C now is going to be 2.133. And then the moment of inertia, which was given to me, is 2.81. And I can find my maximum compression then to be 14.9 KSI. So I'm going to have more compression because it's further away from that neutral axis, but recognize that sometimes materials have different compression, different tension properties. So recognizing going, on the top of the beam, it's under tension. On the bottom of the beam, it's under compression, and applying the equation appropriately.